If I told you that every day over 1 million tonnes of ships are lifted up 87 feet and drop back down again, you'd probably think I'm a bit bonkers. But it's true. I'm talking, of course, about the Panama Canal. I'm sure you already know that it links the Atlantic Ocean at Colón to the Pacific Ocean at Balboa. From above you can see that a huge chunk of the passage passes through Gatun Lake, then the rest is through a series of artificial waterways that have been cut through the mountains at either side. Now, the lake itself sits naturally high above sea level. If you were to open it up to the ocean, all the water would drain away and you'd have to carve an even deeper passage right across Panama. Instead, what happens is that every ship is lifted up 27 metres to the height of the lake. They can then navigate the lake and the mountainous cut until they get to the other side. Once there, they're then lowered back down again to sea level. It makes sense, but it does lead to the question, how do you lift a ship weighing hundreds of thousands of tons up nearly 100 feet into the air? The answer, of course, is locks. The Panama Canal is only one example. You may well have also seen them in smaller canals around the world, or even just at the entrance to ports in tidal areas. No matter where they're found, they all work in the same way. They're basically just a chamber with a gate at either end. When both sides have the same water level, you could literally just pass the ship straight through. If the water on one side is lower, you need to close one of the gates to maintain the difference. Maybe on one side you have an enclosed dock and the tide drops away on the other side, or maybe you have a naturally occurring lake and on the other side you have sea level sitting 27 metres below. No matter, you just close a gate and the difference is maintained. Of course, the water pressure does provide a massive force, so you need to think of that when designing your lock. With the door straight across, an incredible amount of force is applied, potentially buckling gates that are not strong enough. If you place the gates at an angle, however, the force applied by the water is directed along the length of the gate into the walls of the lock instead. The water pressure actually helps to seal the gates and stop them from leaking. So, we now have a situation where there are two water levels, separated by a gate. It's time to get a ship in. Maybe it comes straight in from sea level and then ties up inside the lock. Once in, you can close the gate behind it, separating the lock from the sea. Now, we have three different levels: the sea, the lock, and the internal water. The aim is to just make the lock level match the internal water level. So, quite simply, you just make a hole between the lock and the internal water and the levels will stabilise. Remember, there's way too much force to crack the gates open, so instead, we have sluices. A sluice is just a vertical door that can be lifted up to control the flow of water. Sometimes, sluices are built into lock gates, but often you'll find them bypassing the gates and just running around the side instead. It doesn't matter where they are, but the key is that opening up the sluices allows water to flow from the internal water to the lock. In hydrostatics, it's a concept known as communicating vessels. Basically, if you take a series of open containers containing a homogeneous fluid, assuming they're connected together sufficiently below the fluid level will stabilise regardless of the shape of the containers. In other words, in a lock, when you open the sluices, the water level on either side of the sluices will stabilise. Once it is level, you can open the gate separating the lock from the internal water and the ship is free to pass through. You've lifted the ship up to the level of the internal water. The same exact thing happens in reverse if a ship needs to go the other way. You enter the lock and close the gate behind you, then open the sluices to the outside and allow the water level in the lock to drain away until it matches the level on the outside. When the water levels match, the force holding the gate closed is eliminated so you can open it up and allow the ship to leave. Going back to Panama, the same thing happens but on a massive scale. Instead of just a single lock, each side consists of a series of locks acting like a staircase. A ship enters the bottom one, then is raised up to the level of the second one. It can then move ahead into the second lock where it's raised up to the level of the third one. Finally, it moves into the third lock where it's raised up to the level of the inland lake. The whole thing is powered by gravity, but it's not limitless. Every time you use locks, it costs water. Water flows from the internal level through the locks eventually to the outside. It's one of the reasons for using multiple locks in a staircase. Consider this, a single ship going into a single lock and raising up the entire height. You've used all this water for one ship. If instead you have a series of locks, the one ship enters at the bottom and rises up a third of the way to the level of the second lock. It's used this much water. It then moves into the next lock and you drop the first lock down to take another ship. our first ship rises up again to the level of the third lock and again uses this much water, but this time when we raise the first lock to allow ship 2 to continue, it's using the water that's already been used by the first ship. We don't need to count it twice. Again, the procedure repeats and the first ship rises up the rest of the way, using this much water, and then it's free to move out. The second ship continues its free ride, using the water that's already been counted for the first ship. With the second ship in the final lock, a third ship starts rising up in the first lock, getting even more use out of the water originally spent on the first ship. Now, for the final step with the second ship, it needs to use water straight from the lake to make it the rest of the way, but then it's free to move on, having only actually consumed a fraction of the water for its own passage. Likewise, every ship after that only needs to consume new water for its final step. Effectively, using 3 steps has reduced the average water consumption for each ship to a fraction of that required for a single step. The more steps you have in your lock system, the more you can share water and the less each individual ship consumes. So, why not make 100 locks and use even less water? Well, it then becomes too inefficient as it takes time and fuel for each ship to wait for the gates to open and close and manoeuvre into each lock, but we can simulate more locks instead using water-saving basins. Let's consider a single-step lock. Each cycle you would use this much water. But if I install a water-saving basin alongside the lock, instead of draining it straight out to sea, when it's time to lower down we can instead drain it into the water-saving basin. The level of the lock and the level of the basin will equalise around the 50% mark. Then, you drain the final part of the lock into the sea. When the next ship comes along wanting to rise up, you can start off by using the water-saving basin. The basin and lock equalise around 25% up, so you only need to draw on 75% of the water to fill the lock the rest of the way. Of course, the second time you use the water-saving basin, it starts off quarter full. When the lock and the basin equalise, it's then around 63%. You then drain away the rest of the water to sea. When the next ship comes along, you let the basin and lock equalise, settling around 36% full. Again, fill the lock from the top to get it all the way up, this time only needing 63%. Eventually, once you repeat the cycle enough times, the water-saving basin ends up saving you approximately 1/3 of the water each cycle. Notice how it fluctuates around the middle of its capacity. You don't need the top part or the bottom part as the water never reaches those levels. Of course, you could add more basins in series and save even more water on each cycle. In Panama, they use 3 basins in series for each step of the lock. You can think of it like this. The top 20% of the water drains into Basin 1, the next 20% into Basin 2 and the next 20% into Basin 3. The final 40% drains away. Then, when you refill the lock, the first 20% is from Basin 3, the next 20 from Basin 2 and the next 20 from Basin 1. The top 40% needs new water. Using 3 water-saving basins in series saves approximately 60% water. Combine that with using a series of 3 locks and you can make quite an efficient system depending on your traffic levels. Panama relies on a naturally filling lake, so during the dry season they can have issues with the water level. Other places, for example an enclosed dock, may rely on impounding pumps instead. They might use water in the dock most of the time, then when electricity is in low demand and cheaper, turn on impounding pumps to refill the dock. In tidal areas, if the traffic levels are low enough, they may be able to just open up the dock at high water to let it fill up enough to cope with shipping levels throughout the rest of the tide. The water in the dock would still be maintained enough to keep ships afloat without needing mechanical pumps to keep it topped up. When you delve into it deep enough, locks and lock systems really can be fascinating. And that brings us to the end of today's video. Until next time, thank you for watching, and goodbye.